Okay, in this video we're going to look at the log properties, something called the power, product, and quotient rules, and we're also going to use that to solve some logarithmic equations, also practice condensing and expanding completely, and then we'll also look at some exponential equations, so this one will be a little bit longer. So we're going to go through kind of a brief derivation of these rules. So let's suppose that x is equal to log base b of m and y is equal to log base b of n. And so we're going to go ahead and rewrite that. So b to the x is equal to m, and b to the y is equal to n. So if we multiply our m and n together, our m and m's are going to be b to the x times b to the y. Multiply like basis, we're going to add those exponents, b to the x plus y. So we have m times n is equal to b to the x plus y. And then we're going to go ahead and rewrite this. So the base is b, and mn is going to go inside the logarithm, and that's going to be equal to the exponent of x plus y. So we're just rewriting that. Okay. But at the top here we have x is log base b of m and y is log base b of n. So we're going to go ahead and make that substitution. So we have log base b of m times n is equal to log base b of m plus log base b of n. And that's what's called our product rule. Okay, so now we're going to go for the quotient rule. So we're going to take the quotient. So m divided by n is going to be b to the x divided by b to the y, which is b to the x minus y. So that's what we're going to do with the exponents. We're going to go ahead and subtract them. So we'll say that m divided by n is going to be equal to b to the x minus y. And if we rewrite that as a logarithm, that's log base b of m over n, and that's going to be equal to x minus y, the exponent. Okay, so then again, log base b of m is x, and log base b of n is y, so we'll make those substitution. So we have the quotient rule. Log base b of m over n is equal to log base b of m minus log base b of n. And then finally we have the power rule, so we'll just pick on one of them. So we'll raise m to the r power. M is b to the x, so we'll raise that to the r power. Multiply your exponents. So we have m to the r is equal to b to the xr. So we're going to go ahead and rewrite this. Our base is b. M to the r power inside the logarithm, and that's going to be equal to the exponent, which is xr or rx. The order does not matter. And so what we're going to do is we know that x is equal to log base b of m. So we're going to go ahead and make that replacement. We'll move the r to the front, so it'll be log base b of m to the r is equal to r times log base b of that m there. Just sneak that in, just that out of space, okay? So we'll go ahead and summarize that on the next page here. So here's some log properties. So you have the product rule, so log base b of m times n is equal to log base b of m plus log base b of n. The quotient rule, log base b of m over n is equal to log base b of m minus log base b of n. And then the power rule, log base b of m to the r is equal to r times log base b of m. Now when we're solving log equations, usually what we're going to be doing is we're going to be starting with multiple logs, and depending on what operation we have, we will condense them into a single logarithm. Certainly we're in preparation for calculus, so one of the applications is to take things that are products or quotients and break them up into these forms here, and when we're doing those applications, usually we're going to be doing something like a derivative. That's going to be a lot easier if they're in that form. And certainly for that power rule also. And then we'll also use the power rule to solve exponential equations, and we'll also use it to solve applications involving finance and exponential growth and decay models. So we'll use that power rule quite a bit. So let's go ahead and we're going to run through some examples of expanding and condensing. We'll solve some log equations, and then we'll we'll finish up with solving some exponential equations with unequal bases. Okay, so we're going to go ahead and expand completely and then simplify. Okay, so we're going to look at log of 10 times x, and so if it's regular log there, the base is understood to be base 10. So we're going to go ahead and use the product rule, so that'll be log of x, log of 10 and then plus log of x. I guess the order doesn't matter. Okay, log base 10 of 10 is asking you 10 to what power is 10, and that's going to be 1. So log of 10 is going to be 1, and then we don't know what log of x is, we'll leave log of x as is. Okay, so we did get to do a little bit more simplification after we use the product rule. Okay, so let's take a look at another one. So we're going to look at log of x times z to the third power. So again, we're going to use that product rule because we have the product of x and z to the third power. So that'll be log of x and then plus log of z to the third. Okay, the log of x is all done. There's nothing else we can do with it, but the log of z to the third, you have that exponent of 3, so we can go ahead and bring that exponent down. So that'll be log of x plus 3 log of z. Okay, and then we'll go ahead and pause it for a moment, and we'll mention something that, students often ask about, things like this or this, and they both mean the same thing. We're being extra careful on the left-hand side with the parentheses there. On the right-hand side, the understanding is both the z is inside the log there. So sometimes you'll see with or without the parentheses. If there's only one term there, then sometimes they don't write the parentheses. If there's multiple terms, then usually they're going to put a parentheses there. So anyways, let's go ahead and move on to the next one. So here we're going to look at log base 7 of x times y over 8, and then that's going to be raised to z to the 9th power. So the first thing we're going to want to do is we're going to undo that division in some sense. We're going to use that quotient rule. So it's going to be logarithm of the top, so log of x times y to the 8th, minus log of the bottom, so log of z to the 9th, and that is using your quotient rule. Okay. And so now we can do a couple of things on that first log of x y to the 8th. You do have a product, so we can split that up as log of x plus log of y to the 8th. And then you see that minus log z to the 9th. We can do the power rule on that and bring that 9 down. So this becomes log of x plus log of y to the 8th minus, and then I went ahead and did that power rule to bring down this 9 here already. Okay, so that'll be minus 9 log of z. And we can do one more thing. We can actually do the power rule on the 8 here. And once you get more comfortable with this, you can do multiple steps at once, and sometimes you'll be able to do the whole problem in one step if you get good at it. Okay, so we got log x plus 8 log y minus log z, minus 9 log z, excuse me. Okay. All right, so I think we're going to look at one more here. And we're going to look at log base 4 of 64 over the square root of x squared minus 1. So this one's got a little bit more going on. The primary thing to break up right now is we do have a quotient, so it's going to be log base 4 of 64 minus log base 4 of, and then if you remember, the square root of b is equal to b to the 1/2 power, so the square root we'll rewrite as a 1/2 power, and for the sake of being efficient, we're going to also factor x squared minus 1 into x minus 1 and x plus 1. Okay? Alright, so, and then there's our square root as a 1/2 power. So we got some more stuff we can do here. If we notice that 64 is a power of 4, 4 to the 3rd power is 64, so that log base 4 of 64 becomes 3. On the other log there, the minus log base 4 of x minus 1, x plus 1 quantity to the 1/2 power, we can go ahead and do the power rule and bring that 1/2 down. Okay, and then the final thing we can do is the x minus 1 and the x plus 1, they are attached by a multiplication, so we'll use that product rule. So this will be 3 minus 1/2 times the quantity log base 4 of x minus 1 and then plus log base 4 of x plus 1. And then we can go ahead and distribute that minus 1/2, and that is expanded as we can get. And if we were doing some sort of application in calculus, taking the derivative is one of the things we would do. Taking the derivative of this final form would be significantly easier than taking the derivative of the original problem. So that's certainly where it's going to be helpful. In pre-calculus, you'll do some more of them, probably more difficult than this one, or it should most certainly be more difficult than this. Okay, so that's expanding, so we're taking them all the way apart as far as they can go. Now we're going to condense, which is going to take something in this form here and put it back together. And so we're going to use the condensing when we're solving log equations. Okay, so we're going to go ahead and rewrite as a single logarithm. And oftentimes they'll refer to this as condensing or condense. So we're going to look at log base 3 of 5 plus log base 3 of x and minus log base 3 of 4, and not 0.4. Let's make sure that doesn't look like a 0.4. Okay, and we'll go ahead and do the first two together. Log base 3 of 5 plus log base 3 of x. That's going to be the product rule. So it becomes log base 3 of 5 times x, and then minus log base 3 of 4. Okay, so that was using our product rule. Okay, and then we can go ahead and combine the log base 3 of 5x minus the log base 3 of 4 as a quotient, so the 5x will be on top and the 4 will be on the bottom. And that's as far as we can go using that quotient rule there. Okay, I think we're going to look at 3 more of these. Get a little bit harder. So here we got log base 3 of x plus log base 3 of x plus 6. Or, oh, sorry, not that plus 6. Looks like it's plus 8. Plus 8. Okay, so we're adding logs of the same base, so we're going to go ahead and use the product rule. That'll be log base 3 of x times x plus 8. And so that'll be a log of x squared, a log base 3 of x squared plus 8x. And so that certainly is kind of the type of problem we'll encounter when we're solving log equations combining in this fashion. And we'll go ahead and mention that we did use the product rule on that particular problem. Okay, let's take a look at the next one. Log base 5 of 75 minus log base 5 of 3. So we're subtracting logs of the same base, so we're going to use the quotient rule. So that's log base 5 of 75 over 3. And 75 cents is 3/4, so that reduces to 25. So log base 5 of 25. 5 to the second power is 25, so log base 5 of 25 is the exponent there, which is 2. Okay, we'll go ahead and we'll mention the rule we used there was the quotient rule. Okay, all right, I think we got, I guess this is probably the last one. All right, so we got 1/2 log base 2 of 7 minus 4 log base 2 of x, and then minus 3 log base 2 of 4. The first thing we're going to do is mention, again, we mentioned this not too long ago, but as a reminder, b to the 1/2 is the same thing as the square root. And what we're going to do first is we're going to put those exponents back up. So we're going to put back up the 1/2, the 4, and the 3 there. You do have a choice there. You could put up the minus sign also, but then you're dealing with negative exponents, so I would probably avoid doing that. So just put back the 4 and the 3 there. So this is going to be log base 2, and remember 1/2 power is the same thing as square root, so log base 2 of the square root of 7 minus log base 2 of x to the 4th minus log base 2 of y to the third power. Okay, and that was using the power rule on all three terms. So using the power rule on all three terms. And then we're going to go ahead and combine only the first two. Now, if you get good at this, you can do pretty much the whole problem in one step, or you can do you can skip a little bit. Here we're going to be more thorough. So this is going to be log base 2. We're going to use the quotient rule because we're subtracting logs of the same base. So that'll be the square root of 7 over x to the fourth, and then minus log base 2 of y to the third, and that was using our quotient rule. And we can go ahead and use that quotient rule again because we have log of the same base and we're subtracting them. So that's going to be the square root of 7, and then on the bottom will be the x to the fourth and y to the third using that quotient rule again. Now, I have a little bit of a saying there is if it's positive, it's on top, negative on the bottom, if you want some help remembering where things go. So positive on top, negative on the bottom. Other things to mention is you do need to do those power rules first before you can combine them. When you're combining logs using quotient and product rule, the logs coefficient needs to be 1 or minus 1. Also, they do need to all have the same base. Now for us in college algebra or probably pre-calculus also, you're not going to be running into different bases really, so that won't be too much of an issue. But these rules only apply if everybody has the same base. Okay, so here's that working out that last step with the quotient rule with the fraction there. So it'd be the square root of 7 over the x to the fourth, and then divided by y cubed if we follow the quotient rule. Okay, so that's the square root of 7 over x to the fourth, and we can write y cubed as y cubed over 1. So now we're dividing the fraction by a fraction, so we keep the first fraction, and we flip the second fraction over, and we change this operation from, we change the operation from division to multiplication, and so now you'll have the x to the fourth y cubed on the bottom and the square root of 7 on the bottom, on the top there. Okay. All right, so I think that's the last one of these, and we're going to look at solving logarithmic equations. Oh no, we're not going to do that. Just kidding. I forgot. We got to do the change of base. All right, so log base b of x is equal to y. If we rewrite that, that is b to the y is equal to x. Okay, and I prefer to use the natural log because it works well with e. The e and ln are inverses of each other, and also ln is less writing than regular log. So we're going to derive the change of base formula. And so the natural log is a operation. It is a function, so we can apply the natural log to both sides of an equation. B to the y and x are both positive, so those are valid inputs for the natural log. So we'll go ahead and take the natural log of both sides, and this is kind of like what it's going to look like when we solve exponential equations. And then we're going to use the power rule to bring that y down as a factor. So that'll be y natural log of b equals the natural log of x. Now the natural log of b is just a factor attached to the y, so we can go ahead and divide by that. And so we have the natural log of x over the natural log of b, and that was equal to y, and y was equal to log base p of x. So what this does for us is most calculators only do log base e, which is the natural log, or log base 10, which is the regular log. So this allows us to convert a log of any base into ln or a regular log. Okay, so here's your change of base formula. And so it says log base b of x is the same thing as the natural log of x over the natural log of b, or we can write it as the log of x over the log of b. So those are the two that you'd want to usually write it as, or we can convert it into any valid base, so log base a of x over log base a of b, and the valid base would be greater than 0 and not 1. Okay. So we'll do one example of using the change of base formula. I'll convert it into natural log. Maybe you can check yourself and convert it into the regular log. So we're going to use the change of base formula here. and we're going to find log base 17 of 48, and we're going to round that to 4 decimal places. I don't want to do 48 decimal places. We're going to just do 4 decimal places. Okay, so log base 17 of 48. So that's going to be the natural log of the argument over the natural log of the base. And certainly you can try it on your own, and you can find log of 48 over log of 17, and you'll get the same value here. So we're going to round it to 4 decimal places. So I'm going to put that in my calculator, and I'm going to write down 5 decimal places. I look at the 5th decimal place. If it is 5 or larger, I'm going to round this 3 up to a 4. If this was less than 5, then I would round down and leave that as a 3. So because it's a 6, we're going to round up. And so I say 1.366 and round up to a 4 using that change of base formula. Okay. All right, so that's change of base formula. Now I think we're going to get into solving the log equations. I was so excited about getting into that I forgot that we did also change of base. Okay, so solving log equations. What we're going to do is we're going to isolate and condense the logs. That's using your product, your power, and your quotient rules. And then you're going to identify it as form 1 or form 2. And basically you're looking at, is there a log on one side or a log on both sides? If it's form 1, you're going to rewrite it in the exponential form. So log base b of x equals y is the same thing as b to the y power equals x. If it's in form 2, you're going to have a logarithm on both sides. So it'll be log base b of x is equal to log base b of y. That is if and only if x is equal to y. So sometimes you say equal bases equal exponents. Well, equal bases equal arguments here. It's really using the one-to-one property of the logarithm that gives us this property. It's this way of solving, I guess we can say. So the one-to-one property allows us to do this. And then check your solution. So logarithms need their arguments to be greater than 0. So you just take your argument, set it greater than or just greater than 0, and then run your check with your solutions. So let's go ahead and try it out on a couple of examples. So we're going to go ahead and solve log base 2 of 3x plus 4. That's going to be equal to 4. So this is form 1. The logarithm is, there's only one there, it's isolated. So base is 2, exponent is 4, and that's going to be equal to 3x plus 4. 2 to the 4th is 16, and that's going to be equal to 3x plus 4. We'll go ahead and subtract 4 from both sides, and then we'll divide by 3, and we'll get x is equal to 4. Okay, so x is equal to 4. Now, I'll check this one real carefully, but if you want to check real quick to see if your solution is even valid, fits within the domain, you just take the argument 3x plus 4 and solve that. And so our answer needs to be subtracting 4 and dividing by 3, bigger than negative 4/3. Our answer is 4, so we can probably make the assumption that that's valid. I'm going to go ahead and check it by actually plugging it in, and you can certainly do that with all of them also. Okay, so log base 2 of 3 times 4 plus 4, is that equal to 4? Well, log base 2 of 16 is asking us 2 to what power is 16, and that is in fact 4. So that's a good solution. Okay. All right, so I won't check it this way every time. You can check it this way every time. I'm going to do a little bit of a quicker way of checking for extraneous solutions, and that's taking my arguments and setting them greater than 0. Okay, so log of x plus 8, is it 8? No, it's 5, sorry. Minus log of x plus 2, and that's equal to 2. So the first thing we want to do is isolate and condense the logs. So we do have 2 logarithms, and they're being subtracted, so that means we're going to use the quotient rule. So that's going to be log of x plus 5 over x plus 2. Now, one thing to be a little bit careful of is when we do the quotient rule, you're taking 2 logs and combining them into a single logarithm. So it's you got to be a little bit careful. It is not log base 10 of x plus 5 over log base 10 of x plus 2. And boy, is that an ugly G. Let's make it a little bit nicer. So it's not 2 logarithms. It's only a single one when we do that quotient rule. Okay, and that's going to be equal to 2. And this is form 1 because we have a logarithm on one side, so we're going to rewrite. The base here is 10, exponent is 2, and that's going to be equal to x plus 5 over x plus 2. And don't do anything crazy. It's a regular, it's going to end up being a linear equation. And we're going to clear the fraction by multiplying by x plus 2 of both sides. Distribute the 100, and we get 100x plus 200, and that's going to be equal to x plus 5. Nice linear equation, so we'll isolate the variable by subtracting x and subtracting 200, and subtracting x and subtracting 200 from both sides. So 99x is equal to negative 195. We'll divide both sides by 99, and we will go ahead and reduce, and we get negative 65 over 33, which is approximately negative 1.9697. If I need more decimals, I'll go ahead and do that. Now I'm just going to run my check to make sure it's within the domain of possible solutions. So we're going to go ahead and take our arguments of x plus 5 and set that greater than 0. So on one hand, our answer needs to be larger than negative 5. Negative 1.9 blah 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 is larger than minus 5. And also, it must be greater than, looks like, greater than negative 2, which it is. So this is, in terms of, does it even fit the domain, that is correct. Now, if you want to, you can plug it in and get all the common denominators and whatnot, and it'll work out just fine. You'll end up getting 100 inside the logarithm. Anyways, let's go and run through a few more. So we're going to look at the natural log of x plus the natural log of x minus 6, and that's going to be equal to the natural log of 3x. So first thing to do is to isolate and condense the logs. So we have two natural logs being added together on the left-hand side, so we'll combine them using the product rule. So that'll be the natural log of x times x minus 6, and that's going to be equal to the natural log of 3x, okay? So we've isolated and condensed the logs, and it's form 2. We have two logs, and so we can use the one-to-one property and equate the arguments. So x squared minus 6x is equal to 3x, okay? Don't go crazy on me. This is a nice quadratic. We're going to move the 3x over and then factor out an x. This is not a difference of squares. We don't want to be square rooting both sides. Don't do anything crazy. Just a nice quadratic equation. So subtract 3x. I guess if quadratic equations can be nice, this is a nice one. X squared minus 9x is equal to 0. Factor out an x, and we get two solutions of x equals 0 and x is equal to 9, or x is equal to 9. We'll run our check. So our first argument, x must be greater than 0. X minus 6 must be greater than 0, so x must be larger than 6. And 3x must be greater than 0, so x is greater than 0. Okay, so x equals 0 does not meet the requirement of being greater than 0 or greater than 6, so we throw that out. However, 9 is larger than 0 and larger than 6, so 9 is valid, but 0 we throw out. And if we're putting it in the homework system on the computer, we only put the answer of 9 in. Okay, on the test, you do it exactly like we did. Cross out the 0. Okay. I think we have two more of these logs, and then we'll run over and do some exponential equations. So we have log base 55 of x plus 6 plus log base 55 of x, and that's going to be equal to 1. Okay, so first step, isolate and condense the logs. So we do have two logs of the same base. We're adding them, so we're going to use the product rule. So this will be log base 55 of x plus 6 times x, and that's going to be equal to 1. We have now isolated and condensed the logs, so now we check, is it form 1, is there one log, or is it form 2, there's two logs, a log on each side. This is form 1, so we go ahead and we rewrite it. Base is 55, exponent is 1, and that's going to be equal to the argument of x squared plus 6x. Okay, again, this is a quadratic. Don't do anything crazy. We're not square rooting both sides. Don't do it. Subtract 55, set it equal to 0. Most of the time they're going to be rigged, so they factor. So the 0 is equal to x squared plus 6x minus 55. And that's going to factor into x plus 11 and x minus 5. So that gives us two solutions of x equals negative 11 or x is equal to 5. Now we need to run our check, so we'll go ahead and take the arguments of x plus 6 and x and set them greater than 0. So on one hand, x must be greater than negative 6, and on the other hand, x must be greater than 0. Negative 11 doesn't meet either requirement, so we throw that out. However, 5 is good. Okay. All right, the next one is kind of a cool problem. It's a nested log inside of another log here. So we're going to look at log base 3 of log base 3 of x, and that's going to be equal to 2. Okay, so the logs, this is kind of weird, but the logs are already isolated and condensed, so we do have a composition of two logs, so this is a little bit different, but you can think of it as one log on one side there. It's going to work the outer log. The base is 3, and the exponent is 2, and that's equal to the argument of log base 3 of x. Okay. 3 squared is 9, and it's equal to log base 3 of x. The base is 3, and the exponent is 9. 3 to the 9th is equal to x, and that's a big number. 19,683 is equal to x there. Okay. All right, so that is our last log equation we're going to take a look at. And there's probably some more log equations on some of my other videos there. Maybe you look at some other YouTube videos to take a look at your textbook for more examples if you need some more examples there. So now we're going to take a look at exponential equations, and now that we have that power rule, we can actually solve all the exponential equations before we had to do the equal bases and equal exponents. So here's the guidelines for solving an exponential equation, and we're only going to look at unequal bases. And when we have unequal bases, then we have to use we're going to use the natural log. You could certainly do the other ones where we got the equal bases, equal exponents with the natural log, but it's most likely going to be a little bit more work. So our steps here are going to be isolate the exponential. Or the exponential expression, if you want to call it an exponential expression. I guess that's technically what we should call it. Then you're going to take the natural log of both sides and use the power rule. You could also take the regular logarithm of both sides. You could take the log of any base realistically, but any valid base. But we're going to go ahead and do natural log, and then we'll go ahead and solve it. Exponentials don't have any restrictions, so technically, technically you should check your answer, but for us, we won't need to. We won't need to because we'll assume that we've done it correctly. You can still check it if you want to, though. All right, so we're going to solve 2 to the x power is equal to 41, and we don't have equal bases. So we're going to go ahead and apply the natural log to both sides of the equation. And then we're going to use that power rule, bring down that exponent x as a factor. And then x and ln of 2 are connected by multiplication, so we'll go ahead and divide both sides by 2. And that leaves us with the exact answer of x is equal to the natural log of 41 over the natural log of 2. Okay, so it depends on what we're doing. If it's just a math problem like this, then this is fine. I kind of prefer the exact form. However, if we're doing some sort of application and we're trying to solve for time or an interest rate or something to that effect, then it makes sense to convert that into a decimal. Okay, what do we got? 2 or 3 more examples, and so we're going to progress in difficulty here. So this is the easiest of this type. And notice it was very similar to how we derived the change of base formula, in fact. Okay, so 4e to the x minus 16, that's going to be equal to 6. Now, mind you, the exponential expression is only the e to the x. It's the base and the exponent there, so we're going to isolate that. So the first order of business is to add 16 to both sides. So you have 4e to the x is equal to 22. Get rid of that 4 by dividing by 4. E to the x is equal to 11 over 2. And recall that natural log and e are inverses of each other, so the natural log of e to the x is a function and its inverse composed to each other, so you're left with the argument of x. So we're going to go ahead and take the natural log of both sides, and the e and the ln will undo each other, so we have x is equal to the natural log of 11 over 2. Okay, and that is it there. All right, now what do we got? 2 more. So hang in there. All right, so we're going to look at 4 raised to the 4x minus 3, and that's equal to 46. The exponential is 4 to the 4x minus 3. That is already isolated, so we're ready to go. We'll go ahead and take that natural log of both sides. Okay, so bring down that exponent of 4x minus 3 times the natural log of 4, and that is equal to the natural log of 46. And we do have some choices. I'm probably not doing the most efficient route. However, I'm doing the route that I see most students do and what makes, I guess, the most sense for students. And that is to go ahead and distribute that natural log of 4. There's plenty of ways of doing this, but we'll go ahead and stick with that. So we'll distribute that natural log of 4. So 4 natural log of 4x minus 3 natural log of 4. And that's going to be equal to the natural log of 46. So we're going to isolate that x. So we're going to add a 3 natural log of 4 to both sides of the equation. And now we have 4 natural log of 4 times x. And that's going to be equal to the natural log of 46 plus 3 natural log of 4. And certainly you can do something here. You could put the exponent back up and you can combine those. So there's some things to do there. We're not going to do that here, but it can be done. 4 ln of 4 is attached to x with multiplications. We'll divide both sides by that. And we'll have quite a messy answer when we're all done. Again, there's more you can do, but this is fine as is. So x is equal to the natural log of 46. Plus 3 natural log of 4 all over the natural log of 4 natural log of 4. Okay, and so that is as far as we're going to take it. Let's clean up that parentheses a little bit. Okay, one more. So we're going to look at solving e to the 4x minus 1 equals 2 to the x plus 5. So we do have an exponential on both sides of the equation, so they're already kind of isolated here. So we're going to go ahead and take the natural log of both sides. And natural log and e are nice. They're going to undo each other, so that frees the exponent of 4x minus 1. And we're going to use the power rule and bring down the x plus 5, and then times the natural log of 2. Okay, and so now we got x's on both sides of the equation, so that can be kind of tricky. The strategy is to get the x's on one side and everybody that doesn't have an x on the other side of the equation and factor out an x. So we did something like this when we found inverses in the 3.7 video. Okay, so we're going to go ahead and distribute that natural log of 2. So we'll have 4x minus 1 equals x natural log of 2 plus 5 natural log of 2. And then we're going to pick a side, doesn't matter which side, but we're going to move the x terms onto the left, and we're going to move all the non-x terms to the right. So that means we're going to subtract x natural log of 2 and add 1, and subtract x natural log of 2 and add 1. So we will have 4x minus x natural log of 2, and that's going to be equal to 1 plus 5 natural log of 2. Okay, on the left-hand side, the greatest common factor is an x, so we're going to factor out an x. So factor out that x, and then 4 minus the natural log of 2, and that's going to be equal to 1 plus 5 natural log of 2. Sorry, this looks kind of like an h. Let me make it a little bit nicer. So that is the natural log of 2. Okay, and then we're going to we're not going to multiply. We're going to divide by 4 minus the natural log of 2 of both sides. So divide by 4 natural log of 2, divide by 4 minus the natural log of 2, and so we have x is equal to 1 plus 5 natural log of 2 over 4 minus natural log of 2. And we can leave that there. If they ask us for a decimal, then we can put it into the calculator. The one thing to be careful of is you need parentheses around the top and around the denominator if you put that into your calculator. Okay, so we'll have one more video pertaining to Chapter 6, and we'll look at probably one more video. You know, we'll see how long it is, but we're going to be looking at applications of exponential functions in finance and also in modeling exponential growth and decay. But I think we've done plenty in this video, so we'll see you next time.